WWII Wright was born with aviation on the sand dunes of Kitty Hawk in 1903. Born the December day that Wilbur and Orville Wright introduced flying to a skeptical world with an engine-driven contraption of wood and cloth and wire. For the Wright brothers, 6 years later, formed the little company which grew into the great Wright Aeronautical Corporation at Patterson, New Jersey. Here in the days when but one wing of this building housed the company, America's first high-powered, air-cooled radial engine was developed. Then momentous events proved air power vital to national defense. Soon even the day and night operation of this huge engine plant became inadequate to the needs of defense. So in the spring of 1940, plant number 2 was built nearby in Patterson. Under this one roof on one floor are acres of manufacturing facilities designed expressly for the line production of aircraft engine parts. Erected and put to use in the incredibly short time of 57 working days, this plant doubled the output of Wright engines. In the same year was placed in operation plant number 3 on the Passaic River at Fair Lawn, New Jersey. Here also was built the nation's first magnesium foundry for the exclusive manufacture of castings for aviation engines. For even the tremendous rise in production in the other Wright factories proved insufficient to fill the mounting orders. Still not enough, a 4th, and then a 5th factory were acquired. Yet greater than any of the company's Patterson facilities is this gigantic plant at Cincinnati, Ohio, the largest aircraft engine factory in the nation. Here at peak operation are produced high-powered engines in unbelievable numbers. Down the long length of the main machine shop and assembly building stretched line after line of massive machines, thousands of high-speed tools, most of them designed especially for use here, many of them never before employed in the building of aircraft engines. Engine parts travel progressively along these rows of machines, laid out for maximum efficiency according to the latest in-line methods of mass production. Wright engines are not the creations of any one or even a few men. They are products of 1,000 trained minds, of research and test and patient development. They are the essence of infinite ideas contributed by engineers skilled in all the myriad aspects of engine construction. Still other engineers proficient in manufacture transform drawings of improved parts into quantity production realities. They deal with cost and number, with tools and machines, with jigs, fixtures, and gauges, and the minute details of production. Of the more than 10,000 different parts in Wright Cyclone and Whirlwind engines, we obviously can show but a few of the 100,000 operations involved in their manufacture. Yet from these few, starting here with the cylinder head molding machine, you will discover the source of the reliability and high performance of Wright engines, the ingredient of perfection that is built into every part of every engine. Beginning with the making of the intricate coat, the molding of Cyclone cylinder heads is one of the finest examples of sand casting in the world. By means of remarkably deep and closely spaced fins, Wright provides uniform cooling over the entire combustion chamber, cooling which effectively prevents the hot spots that can be a source of detonation in engines of such high power. Pioneers in this field, Wright casts aluminum, magnesium, and bronze to precision and quality standards never successfully met elsewhere. Yet in the great foundries with their 25-year background, there is also quantity production. The Cyclone 14 engine, starting here in the foundry, requires the making of 28 molds such as this for the cylinders alone. Into all these and other molds in this department go each year 100 million pounds of special sand mixed and blended with oil and other substances. And day by day that figure is growing. There is no substitute for the experience on which these production methods are based or the skill which enables this foundry craftsman to carry them out. It is a case of knowing the fundamentals. Today, the immense Wright foundries are in high production as the tempo of engine building speeds up with national defense. The cores inserted into the cylinder head molds are accurately located and checked by gauges. Also made of sand, They serve to form the inside shape of the head, and their correct position ensures a uniform thickness of the walls in the finished casting. Previously dried and hardened for 7 hours in a baking oven, the molds and cores are now given a smoothing coat of carbon by the expert application of an acetylene flame. Assembled next, the molds are placed in groups of 4 on a huge roller conveyor. Molten aluminum, millions of pounds a month, pours day and night into the endless parade of molds. And as each 4 molds are filled, they are rolled forward on the conveyor to cool, making way for the next group. Thereafter, knockout men break open the mold to liberate the new-made cylinder head. Rough yet and stained with soot and burnt oil, it is nonetheless brilliant evidence of the notable skill of Wright foundrymen. Once the excess metal has been sawed off, the rough castings are cleaned with rotary files, some driven by electric motors, others by pneumatic tools running at the incredible speed of 21,000 revolutions a minute. From the foundries, the cylinder heads pass into modern machine shops with lines of production machinery 3 city blocks long, shops with thousands of machine tools of every conceivable type and description. Through them flows a veritable river of metal, hundreds of thousands of engine parts a day, each part a masterpiece of precision. Here a high-speed milling machine cuts the rough cast metal from the tops of the cylinder head rocker boxes, leaving a smooth, finished surface. Multiple spindle drills rough and finish drill and ream the valve guide holes and form the counter bores for the valve seats. Indexing automatically, one piece is completed with each 1/6 of a revolution of the machine table. Cylinder barrels weigh 15 pounds in their finished state, but they begin as 60-pound forgings of nitralloy on giant machines that turn and face and bore 5 barrels at once. Each of them circles the machine in 7.5 minutes, undergoing a different operation at every station. Finally, at the reloading point, the machined barrel is removed and replaced with another rough forging. After further machining and grinding, the barrels arrive at automatic tin plating machines. First cleaned chemically, they are tin plated, again washed and rinsed. And here at the end, jets of compressed air dry them inside and out. Now the cylinder barrels, 54 to a load, are placed in big porcelain-lined containers for nitriding, a process wherein they are heated in ammonia gas to 1,000 degrees Fahrenheit. The outside of the barrels, protected by tin plate, will not be affected. But the inside cylinder walls, from which the plating has been removed, will become hard enough to cut glass, more than hard enough to resist piston ring wear. 3 of these containers form a nitriding charge, and when the process is completed on one, the 50-ton furnace rolls ponderously forward to cover the next charge. This operating procedure keeps the furnace running continuously without costly losses of heat. Each charge, 4.5 tons of cylinder barrels, remains in one of these electric furnaces about 35 hours. Then a 10-hour cooling period ends the nitriding operation. More turning and grinding and the barrels reach automatic lathes where their cooling fins are cut to a thinness but 7 times that of a human hair. No time is lost awaiting sharp tools. The 43 separate tools used here are set up in a magazine holder that can be replaced in a few seconds. To obtain absolute accuracy, the threads by which the barrel is later secured to the cylinder head are finish ground on automatic precision thread grinders. Pouring off the machines in a never-ending stream, the completed barrels stop momentarily for still another inspection. The potential power represented here is staggering and reassuring as well. For in a matter of hours, each barrel will be in a Cyclone cylinder producing 125 horsepower. From adjacent electric furnaces operating at 600 degrees Fahrenheit, hot cylinder heads are taken for assembly to the barrels. The valve seats and guides, previously chilled in dry ice, are inserted first into the heated aluminum head. As it cools, the shrinkage will result in a leak-proof fit of these inserted parts and the barrel. Here also is an example of the skill of the men who build Cyclones and Whirlwinds. Sure-handed, working without effort or waste motion, they are thorough masters of their particular task, an operation ending with the screwing of the cold barrel into position, and the verifying of its proper depth by a gauge check. The cylinder bore is now ground to an extremely smooth finish. However, it is left about 1/1000th of an inch undersized to allow for the final honing operation. This follows numerous painting, paint baking, and cooling processes. Finally, in hydraulic honing machines, the cylinder barrels are brought to exact internal size by fine abrasive stones. These work with a rotary and reciprocating motion. Thus is produced a flawless, glass-hard surface so smooth that it can be measured only in millionths of an inch. Equally deserving of its acclaim as a masterpiece of the machinist's art is the Cyclone 14 crankcase, the engine's rigid center of power. Like every other part fabricated in the shops of Wright, it is the ultimate design in the long series which preceded it. Destined to contain the principal operating mechanism of the engine, the crankcase is composed of 3 main sections externally machined as a unit to attain perfect alignment. In the immense Wright gear departments are manufactured every one of the 425 different gears used in Cyclone and Whirlwind engines. Gear cutting machines by the hundreds, running day and night, turn out gears varying in size from 1/2 inch to 15 inches in diameter. Many of these must transmit the full 1,700 horsepower of a Cyclone 14, a demonstration of strength which gives some idea of the priceless elements of care and quality built into Wright gears. An instance is the care taken after the gear cutting operation to eliminate even microscopic inaccuracies. This consists of grinding the teeth on these special machines. The gear teeth roll against the edge of the grinding wheel in exactly the same manner that they will roll against the teeth of another gear in the engine. The shape of the tooth is thus formed as nearly perfect as human skill can devise. Cyclone crankshafts are assured of a high degree of dynamic balance. This machine detects the slightest unbalance while the crankshaft is rotating. Moreover, it determines the exact point at which correction should be applied. Tester and inspector alike must be satisfied with the balance before the shaft is stamped approved. Precision is the outstanding characteristic of every Wright engine part. It is determined primarily by the accuracy of the tools and gauges used in production and inspection, and it is founded upon the quality of tool inspection. This is the task of men to whom accuracy is almost a religion, of men who have devoted the greater part of their lives to tool making, the job of men whose standard is perfection. Optical and electrical gauges, supermicrometers, dial indicators, Johansen blocks, familiarly called Joe blocks, with a guaranteed accuracy of 4/millionths of an inch, these are their daily working tools. Speed plays no part in this work. Every move is deliberate and executed with care. By the standards of these men, a tool which is nearly right is completely wrong, for only absolute accuracy is tolerated in the tool inspection department. Even with the most careful examination of manufacturing tools, dimensional variations occasionally turn up in the engine parts. Therefore, every single part, regardless of size, is subjected to a wide range of inspections both during and after fabrication. For example, gear teeth are tested on sensitive involute checking machines, which plot their findings on special charts, a permanent record of the gear. Women, too, contribute their skill to our vast program of arming for defense. Their nimble fingers are admirably suited to the swift handling of the thousands of small parts which daily come to them to be checked against Wright's exacting standards. On all highly stressed steel parts, magnetic type inspection is employed, a process in which a liquid containing iron oxide is poured over the highly magnetized part. Any flaw will then stand revealed as a black line, even flaws fine enough to defy detection under a powerful magnifying glass. A Cyclone 14-cylinder engine contains over 8,000 separate parts, and more than 50,000 inspection operations are performed on the parts and the assembled engine before it leaves the plant. Special gauges for each part, X-rays, semi-automatic high-precision checking devices and scales. These are among the tools of the men in control of quality during every step of production. To inspectors whose watchword is perfection, no expenditure of care is considered excessive if it contributes to the reliability of Wright engines. Here there are no shortcuts to safety in the air. On the acres of benches and stands in the assembly department, the handiwork of the engineers who plan and direct production becomes increasingly apparent. As the 8,000 parts for each Cyclone 14 engine reach this department on schedule, some 80,000 machining operations and tens of thousands of inspections have been coordinated in their fabrication through scores of shops and 3 foundries. Parts are joined first in minor assemblies. These in turn meet and grow into still larger ones as they move in planned order down the long lines of sub-assembly benches to the engine stands. Then on the stands, a major section takes form in the manner of this Cyclone 14 crankcase. Here in the power section is revealed the secret of the radial engine, 12 articulated connecting rods working on 2 master rods. Here, too, in a Wright development is the secret of unprecedented smoothness, the dynamic dampers which, through their pendulum-like action, nullify the torsional vibrations of the crankshaft. Already assembled in this last section to go on are the valve actuating mechanism and the gears that drive the engine's accessories. This completes the biggest of all engine sub-assemblies, a section of 500 individual parts. Now on mobile stands designed by Wright engineers begins the final assembly of a Cyclone 14. Begins with the mounting section carrying the lugs that later will secure the engine to the aircraft. Next comes the power section whose pistons, rods, and cranks will convert the engine's reciprocating power strokes into the rotary motion needed by the propeller. The front section of the crankcase is put on with the same care as the other sub-assemblies because of the closeness of the fit. No gasket is used between the crankcase sections, their mating surfaces having been so accurately ground that even oil cannot leak through the joint. Now oven hot, this big gear which drives the propeller speed-reducing mechanism soon cools in place to a shrink fit on the crankshaft. An inspector, as at every other step in the assembly, takes over, checking the seating of the gear and the alignment of the timing marks. This exclusive Wright Uniflow piston, with its compression rings and grooves tapered to prevent sticking, is designed for efficiency and durability. The piston pin is locked in place by a coiled spring. A special run-in compound is brushed over the piston to act as a lubricant while the engine is turned over in the assembly process and during the first few seconds of running. The cylinder is assembled as a unit complete with valves, triple valve springs, and washers. The exhaust valves, forged hollow, are cooled by their filling of metallic sodium. Solid intake valves are cooled by each fuel-air charge passing over them. The 20 nuts which hold each cylinder to the crankcase are tightened equally and accurately by a precision torque wrench, a tool indicating the amount of pressure applied. So skillfully have the assembly stands been designed, and so nicely balanced is the engine about its mounting plane, that it can be turned over on the stand with little effort and without the use of special apparatus. Contained in this assembly is the supercharger and a host of gears which drive the generator, the magnetos, the gun synchronizers, and many other accessories. The engine's ignition wiring is completely enclosed in this one-piece metal shielding harness, a covering which prevents the high-tension currents from causing interference with the plane's radio. Odd as it seems, there's a reason for mounting the carburetor in this awkward upside-down manner. Here a drop washer falls harmlessly to the floor. Mounted from above, it may slip unnoticed into the engine with disastrous consequences. 2 magnetos, light in weight, powerful in action, and designed especially for high-output engines, are mounted in turn on the rear of the Cyclone. From these and many other assembly lines, scores of engines of different types are wheeled daily to the test cells, where they prove their ability to perform. Whirlwinds with 7 and 9 cylinders, the engine which has blazed trails around the world and to the North and South poles. Cyclone 9s, the power plant with a background of 500 million miles of airline transportation over every sea and continent. And Cyclone 14s, 1,700 horsepower for national defense, the world's foremost engine of its type. Test cells, tall towers like these, honeycombed with sound-absorbing baffles. Inside the cells, engines from the assembly lines are mounted on the test stands. Connected are fuel and oil lines, the controls, and the multitude of instruments employed to check the performance characteristics of each engine. Meanwhile, in adjoining control rooms, the test engineers take their stations. A finger jams down on the starter button, and another Cyclone comes to life with a blast of power. Then for 7 long hours it thunders through its paces, all conditions from idling to full power. Thus is tested millions of horsepower each month. The test over, every engine comes down again, its hundreds of units washed and spread out on wheeled tables, 3 to an engine. A corps of experienced inspectors thoroughly examine every single part for evidence of wear or scoring. If either condition should be found, the imperfect part is replaced and the engine is reassembled and retested exactly as though it were a new engine. However, if perfect, the original parts are reassembled without change and the engine is sent on to its final acceptance test run. With the checking of serial numbers against the packing list, here in the packing room, Cyclones and Whirlwinds undergo their final inspection as they rest in the cradles of their shipping boxes. Thoroughly washed in gigantic machines, next coated inside and out with a rust-preventing compound, the engines are finally wrapped in protective sheets of oilcloth stapled at the edges. Then when the massive covers of the boxes are lowered into place, powerful lift trucks haul them off to the shipping platform. Here begin journeys to every free land on earth, by road and sea and rail, journeys that end only to begin again on swift wings. Swift wings powered by Wright. They unite America with a vast network of broad airways. Their speed has made a nation into a neighborhood. Their performance exceeds 1 billion passenger miles a year. There is no barren land so wide, no mountain so high, no sea so vast that the aircraft of commerce cannot span it with safety. Their pioneering has developed markets for our industries from Alaska to the Argentine, and they are destined in the days of peace to open a new era of world trade. Our country's airlines have written into the history of transportation an unprecedented story of high achievement, an exciting record well called a century of progress in a decade. Giant clippers speed across the enormous reaches of the Atlantic and the Pacific Oceans. Linking continents, they make it possible for air travelers to circumnavigate the globe in scheduled aircraft powered by Wright. Today, however, commerce and industry are but means to America's objective, the protection of the nation, an objective which calls for air power second to none on earth. Air power begins in the factories, and the military and naval aircraft which roll off the production lines throughout the land are unexcelled in flight and striking power. Air power becomes effective on 1,000 training fields, flight schools where groundlings are transformed into airmen ready for battle. But wherever men build air power for national defense, wherever men serve in the air arms of the Army and Navy, the Marine Corps and Coast Guard, or in the ships of commerce, in these places, Wright engines are performing their military or peaceful missions with reliability and distinguished service. In all these ways, the Wright Aeronautical Corporation is setting the pace of production and performance for the air supremacy of America.